Everyone. So this is the last day of the conference, and with this first session, we have two talks, and the name of the session is Classification of Design and Components. The first talk will be given by Sharam Razuldadeh, and it is entitled Classification of all T-resilient Boolean functions with T+4 variables.
Hi, everyone. Good morning. Thank you for attending. I was not expecting this many people. So I'm going to talk about my recent work about classification of T-resilient functions with T+4 variables. And this research was done when I was still in Radboud University in Nijmegen. So I will give first some preliminaries and introduction about T-resilient functions, and then I will go to how the approach that we present in this work for classification of T-resilient functions. Consider this stream cipher. It is built by n LFSR, and then there is one generator matrix, generator function F, and based on that, it produces keystream Y. In some cases, attacker is able to fix output of one or a couple of these LFSRs and observe the keystream Y tilde. And by comparing distribution probability between Y and Y tilde, he can find out some secret information about this stream cipher. Resilient functions are kind of countermeasure to resist this attack, which is called correlation attacks. And that is, this F function is T-resilient function if by fixing any T input variable to any fixed variable, any fixed constant, the distribution probability of Y tilde and Y is the same. And these functions were introduced in 1984 by Siegenthaler, and just 1 year later, they found that this definition is equivalent to F, a balanced Boolean function F is T-resilient if and only if the Walsh transform in the points U with Hamming weight at most U is always 0. And if you don't know what is the definition of Walsh transform, you can use this formula for this transform. Other thing in studying Boolean functions is defining the proper equivalence relation. For our case, we use extended variable permutation equivalence, and it is defined in this way. Two functions f and g are extended variable permutation equivalents if you can get one of them by using some constants in the input and output, and also being able to shuffle the variables in the input of first function. For each class of equivalency, we use a representative function to define that class, and we usually use the lexicographically smallest one as the representative. It is kind of trivial to show that if two functions are equivalent under this relation, they will have the same order of resiliency. So based on this, we only need to study representative functions up to this equivalency, not all the functions. In the same paper, where Siegenthaler introduced the resilient functions, he also showed the main weakness of resilient functions, and it is the algebraic degree of these functions. If f is a T-resilient function, then its algebraic degree is limited by n minus t minus 1. And in the case of highest resilience order, it will be an affine function. And based on this lemma, he was able to show the only highest the only Boolean function with the highest resilience order n-1 is the linear function which XORs all the input variables. And also about the second highest one, n-2 resilient function, it is again linear function, but instead of all, one of them are excluded. But this is not kind of useful in this scenario of using as a generator function. He also introduced a very important theorem, which is used in almost all the following works about resilient functions. And it is consider that you have two Boolean functions, the two T-resilient Boolean functions, and you want to build a Boolean function with higher resilience and with one more variable. So consider F to be with n+1 variables, and F0 and F1 is the composition of F following this equation. This is like a unique, so one-to-one mapping from both directions. F will be T+1 resilient function if and only if both F0 and F1 to be T resilient functions. And also for any point alpha with Hamming weight T+1, Walsh transform of both F0 and F1 is equal except for their sign. That has to be different. One trivial solution for this is that considering we have F0, which is a T-resilient function, by putting F1 to be the complement function of F0 in the output, F1 also will be a T-resilient function, and then by this composition of Siegenthaler construction, F will be T+1 resilient, and its representation will be just extension of F0 by adding one extra variable at the output. Later in 1991, Carl et al. Were able to, based on Siegenthaler's construction, were able to classify all the n-3 resilient functions, and they showed, excluding two previous ones with higher order, higher resilience order, there are another 5 functions with resilience order n-3. And this within these 5 functions, the first one is the linear one, which doesn't include 2 of the variables. And the other 4 ones are quadratic functions. About n-4 resilient functions, we didn't know much before this work. The only thing was based on a theorem by Tarnikov and Krynikov in 2000 that they showed any n-m resilient Boolean function, n-m resilient Boolean function with n variables can be only in the form of this equation. So only Q variables can appear non-linearly, and rest will be only linear addition. And this Q is limited for a fixed m. For instance, for m equal to 3, this number is 4. We can, so here there is no nonlinear variable. Here there is only 2. Here 3. Here again 3, and here 4. So any n-3 resilient function can have only at most 4 variables to be included nonlinearly. And they were able to show for the case of m equal to 4, it is 10. So we only need to classify n minus 4 resilient functions up to n equal to 10. The rest will be just a type 1 extension of these functions. These were everything that we know about them, but in our work, we introduced a new algorithm to classify all the n minus m resilient functions based on Siegenthaler's construction. So just a short recall, we put all, let's consider we have the set of all T-resilient functions with n variables, and then we try F0 and F1 and check for the second condition in Siegenthaler's theorem and see if the composition is T plus 1 resilient. But as I said previously, we don't need to find all of these functions. We only need to find the representative functions, and we show them by this R star. And also, based on the trivial solution for this construction, we know all the type 1 extension will be included in Rn, the set of R with n plus 1 variables and T plus 1 order of resiliency. So we only need to find the ones that are not type 1 extension. And just short notice that the computation complexity of this basic approach would be trying all the possibilities for F0 and F1. So like size of R to the power 2. But we showed that F is representative if only F0 is representative. So for F0, we don't need to go through all the T-resilient functions. We only need to go through all the representative resilient functions. So complexity would be R size of R star and then multiplied by size of R. But this needs to save all the set of R, simple R, and this needs a large memory. So what we do is instead for F1, we choose a representative and we go through all the equivalent functions to F1. And this increases a bit the time complexity, but the memory cost would be negligible by these changes. The other, we also use other 3 techniques to reduce the number of representative pairs for F0 star and F1 star. And the first one is that if F0 is a representative function, there will be no F function composed by F0 and any F1 that can be in the set of representatives and also be not type 1 extension. So for our search, we don't need to go through all the, for F0, we don't need to go through all the representatives. We only need to check representatives which are not type 1 extension. There is a technique too, but it is a bit complicated. I suggest you check it in the paper if you are interested. But the technique 3 we used is that in the Siegenthaler's construction, the 2 function F0 and F1 from set of R can form a function in set of R with 1 extra variable and 1 higher resilience if and only if these 2 multisets are equal. I emphasize that these are not sets but multisets, and it is the magnitude for the Walsh transform of representatives for both these functions has the same distribution. Based on this lemma, we can, in the start of the step for building all the representative functions with n+1 variables and t+1 resilience order, we compute these multisets for each representative, and when we want to pair them, we only do for the two functions which has same this multisets. Just a head up, for the case of n variable, n+4 variable functions with no. For the case of T-resilient functions with T+4 variables, number of representative pairs we need to is shown here. So in the first row, it is just basic approach. And as you see, this number by increasing n will decrease all the time. But only with using technique 1, all the numbers are decreased, and by increasing n, they are increased by, but in between, they are again reduced. And adding technique 2 and technique 3 for each fixed n, the number of representative pairs are reduced significantly. So our techniques for the for reducing representative pairs are only these three techniques. So consider that we chose one representative pair that is already filtered out by all these techniques. Now we need to check all the permutations P and constant A and B. And then we check if this equation holds for all the alpha points with weight T+1. And if this holds, we know their magnitude would be the same. But we have this equation for between F1 and its representative F1 star. And if we put it in this equation, we will have a equation based on only P and not A and B. So when we choose the representative pair, we first go through all the possibilities for P and check if this equation holds for all such alpha points. And then we go through all the alpha and A and B. But it will be very few number of possible P's for this choice. So to summary, there are more detailed techniques used in the paper. If you are interested, please check it. To summary the paper, in this work, we classified all the T-resilient functions with T+4 variables, and we showed there are only up to the equivalence, there are only 761 such Boolean functions, such representative Boolean functions. And we try to classify T-resilient functions with T+5 variables. And we find out for the case of 6-bit Boolean functions with resilience order 1, there are about 2 to the 30 such representative functions. And we were not able to go farther because of memory complexity and time complexity problems. Yeah, that's all. Thank you.
Thanks a lot. Do we have questions?
It's early in the morning.
If not, in the paper, you say that this type of construction could be interesting for side channel, in the side channel scenario,
Yes.
like for a new design, and that would resist well. Do you have in mind, I mean, is it one of your future work to use this to build one and to have a new design?
Honest, no, because I came up with this classification because I was interested to build some S boxes with higher order branch number. And then it was kind of related to resilience order functions. And so I thought maybe I need to first classify all these functions and then go further to build such functions. This was the reason how I came up with this functions. Yeah.
Okay, thank you. Any other question? If not, let's thank the speaker again. Okay, so the second talk is entitled Equivalence of Generalized Pestel Network. This is a paper by Marie Euler and Patrick Derbez, and Marie is giving the talk.
So hi, thank you for this introduction. I'm Mary, and I'm going to talk about generalized Pestel networks that I will call GFN for short. So let's first look at GFNs. So at the beginning, there was the Pestel network, the one that has been standardized in the DES in 1977, and the one that has been used in so many block ciphers since. So in this design, the state is divided in two parts, two equal parts that are called branches, and at each round, the left branch enters in a nonlinear function, and the output is XORed to the other branch. And then the two branches are swapped. This has a lot of good properties. For example, decryption is really similar to encryption. And also you can have some proofs that it transforms a pseudo-random function in a pseudo-random permutation. However, in the original design, there is only two parts, so these parts can be quite big, and then you have to design a large nonlinear function. So people thought that maybe you can split the state in more parts, and this led to generalized Pestel networks. So there has been several propositions. Type 1 is a really a light update function where only one branch is updated at each round, so you need a lot of rounds to prove any security results. Type 2 is a more balanced update function. And type 3 is a really strong and a heavy update function where all the branches are updated at each round, but it's not really efficient because you can't compute it in parallel. So most of the following works use the type 2 GFN. You can notice that in all of this design, the swap of the branches has been replaced by a cyclic shift of the branches. Later on, people noticed that this cyclic shift is not really efficient for diffusion. So Keisha and Eichberg had the idea to replace this cyclic shift by another well-chosen permutation in order to improve the diffusion. And then in 2010, Susaki and Minimatsu introduced a more generic framework where you can use any permutation to shuffle the branches, and then your GFN is merely described by the Pestel step with the nonlinear function and the XOR, and the permutation P, so you can denote it as PF to the R for R1s. This is quite a large framework, so most of the following works only focused on even-odd GFNs, that is GFNs for which the permutations sends left branches to right branches and right branches to left branches. The main advantage of this even-odd permutations are the fact that every branch enters in a nonlinear function at least every 2 rounds. Moreover, this kind of permutations can be described by two smaller permutations, the one of the left branches and the one of the right branches. I said we can use any permutation in a GFN. However, all of them are not good. Some are better than others, and we have two main criterions to determine which one are the best. The first one is diffusion round. So it is a minimum number of rounds such that all the output branches depend on all the input branches, and conversely. This has a lot of interest in integral cryptanalysis, impossible differential attacks, and meet-in-the-middle attacks. It is quite easy to compute via linear algebra. And for the case of cyclic shift, it is equal to the number of branches. The other criterion is the number of active S boxes. So here we do the abstraction of that the nonlinear functions are black box, and that brings confusion, and we call them S boxes. And we want to count how many of them are active in any differential or linear trails on R1s. And this is linked with differential and linear attacks. The most generic way to compute it is via MALP, and so it's much harder and takes longer to compute than the diffusion one. There has been several designs of block cipher based on GFN. So before 2010, they were using the cyclic shift of the branches. So we had Clefia and height with 4 and 8 branches, and a diffusion one that is equal to the number of branches. And then in 2011 and 12, there has been L-block and Twine, which are GFNs with 16 branches and a diffusion one of only 8, which is achieved by a more complex linear layer. And more recently, Warp is a block cipher that has been introduced with 32 branches and an even more complex linear layer with a diffusion round that is only a third of the number of branches. So in all of these designs, one of the first steps for the designer was to find a good permutation. And this is a really difficult problem because the search space is really large. So let's recall that there's factorial 2k permutations of 2k elements, and that in the even odd case, we have the square of factorial k possibilities. So for the case of GFN with 32 branches, these are spaces that can't be explored. So there has been several strategies in order to find good permutation. In 2010, the idea was merely to enumerate all the permutation, and the authors could go up to 16 branches. And then two techniques have been introduced, equivalence classes and tree pruning, and we could go up to 36 branches in the even odd case. However, all of these strategies are using a greedy strategy. They are searching for permutations with a good diffusion round, and then among them, trying to look for some with a good number of active S-boxes. And it has been shown that this strategy is non-optimal. So we want to look at even more larger spaces. So let's now dive into the subject of the article, that is equivalences between permutations. And there has been a previous work in 2019 by Koshua, Gomez, and Thomas. And the idea is to notice that the Festel step acts similarly on all the pairs of branches. So any shuffling of pairs commutes with this step. And so they introduced the notion of permutations of pairs, that is permutations that shuffles pairs of branches together. And when you do this, you notice that you have, I don't know if I have a pointer. Sorry. If you look at R1s of the GFN associated to P, it is equal to R1s of the GFN associated to any conjugate of P via a permutation of pair, up to a relabeling of the inputs and the outputs. So that's why they say that any permutation is equivalent to all its conjugates via a permutation of pairs. This leads to a more efficient enumeration of even-odd GFNs, because now you can associate any even-odd permutation to a whole family of other even-odd permutation, and you only have to pick one of them in your enumeration. So the enumerations go from the square of factorial k to a factor of factorial k. And for the example of GFN with 32 branches, you don't have to study 2 to the 88 permutations, but 2 to the 52. So it's still quite large. However, even if this reduction is interesting, it doesn't cover all the case. For example, we can look at this example. On the left, we have a really naive GFN, where the left and right branches is merely the identity, with left and right branches permutation. And on the right, we have a more complex GFN, where the left and right branches permutation is a cyclic shift. The cyclic shift is not a conjugate of the identity, and so these two GFNs are not conjugacy-based equivalents. However, if we look more closely, we notice that the output after 3 rounds of these two GFNs is exactly the same. And if we look at intermediate rounds, we can relabel the output and obtain the output of the other GFN. So we want these two GFNs to be considered as equivalent. So what we do, and the thing that we want when we say that they are equivalent, is that we can relabel the input and output of one and obtain the output of the other GFN. But we relax the constraint on the output relabeling so that it can depend on the rounds. You don't have to, you don't need that it is the same for all the rounds. And we can write it at the level of permutation as a constraint on the permutations that has to be permutations of pairs. Let's look at two simple examples. So the first one is when the two permutations are mainly conjugate via a permutation of pair, then the output relabeling is the same for all ones. So it was a previous idea. But you have also other cases, for example, with Q is B times P, where B is a permutation of pairs that commute with P. Then you don't need an input relabeling, and the output relabeling is merely the powers of P. So now we have a larger equivalence relation, and so the number of elements in each classes is bigger, and you have less equivalence classes. We counted them in the paper and show that there are factorial k expanded equivalence classes, and each of them contains factorial k permutations. So for 32 branches, we now have to consider 2 to the 44 permutations. The proof is quite technical of this result, so if you want, you can look at the paper. But one of the main tools in it is noticing that in these new equivalence classes, the cycle structure of the difference of the left branch permutations and the right branch permutation is invariant in the equivalence classes. And that's why we chose to describe even-odd permutations by the difference of the permutations and one of the original permutation. And this helps us to regroup permutation together in the proof. So let's now look at some applications of these equivalences. So the most direct one is looking at previous paper, where a long list of candidates for GFNs with good properties are given. And in fact, this list are quite redundant, and we reduce them. So for example, in 2018, there has been 16 permutation suggested in order to improve the resistance of the block cipher L block against Dimitrov meeting the model attacks. But in fact, there are in only 2 classes. So you could have given only 2 permutation. And here we introduce a notion of extended equivalence classes, where extended means that you consider that a permutation and its inverse are equivalent because they correspond to the encryption and decryption of the same GFN. The second application is the case of warp. It was one of our motivation for this work. And in warp, there is a 32 branch permutation. The designer found it by looking at the structured spaces of candidates, among which they found 152 permutations with a diffusion round of 10, and among them, 8 permutations with a number of active S boxes greater than 64 after 19 rounds. However, they noticed that for these 8 permutations, they always behave the same for large class of attacks, and they couldn't find which one was the best one, even if they are not isomorphic. So here, isomorphic means a bit the same as conjugacy-based equivalent. We computed them again, and we noticed that they are extended equivalent. So this explains why no difference could be found between them. We go further, and we regrouped the 152 permutations in only 7 classes. And so we could compute the number of active S boxes on only 7 permutations instead of 152, so the computations is quicker. We even go further and consider a larger space of permutations, which reduced to 184 classes with diffusion round of 10, and found among them 5 classes of permutations with a number of active S boxes greater than 64 after 18 rounds. So it's 1 round less than the one in warp. The last application is a new family of GFNs with good diffusion properties. So here I draw in blue the Fibonacci lower bound. That is the lower bound on the diffusion round of GFNs. And in gray, it's a space where if you draw a large number of permutations at random, they belong. It's really hard to be in the white space. So there has been a previous family of permutations with good diffusion rounds that is based on De Bruijn graphs, but it works only for number of pairs of branches that are power of 2. We introduced a new family that we call pseudo-cyclic permutations that works for any number of pair of branches and behave well regarding diffusion properties. It seems to behave the best for a number of pair of branches that are prime. So we mark them with square here, and if it even reaches several times the lower bound. So to conclude, this work brings a better understanding of the fundamental structure of type 2 GFNs because we notice that we can consider the difference of the permutations and so on, and we count the equivalence classes. And we also introduce new GFN candidates that are good regarding diffusion or the number of active boxes. However, there are still a lot of open questions, so we didn't deal with the number of equivalence classes in the non-even-odd cases. We'd like to find other good permutations and study more the ones that we have presented. And last idea would be to do some security analysis with this, because for a large class of attacks, they are invariant in the equivalence classes, but some are not, and I will explain it before concluding. Let's look at invariant subspace attacks. We have two equivalence GFNs here. On the left, the GFN has a lot of invariant subspaces, for example, the first two pair of branches. And on the right, it has no invariant subspaces, but it has subspace trails. And subspace trails are much harder to find than invariant subspaces. So maybe an idea would be to look at invariant subspaces in equivalent GFNs and then convert them in subspace trails in the original GFN. Thank you for your attention.
Thank you. Are there any questions? Yes.
Thanks a lot for a very nice talk. Just a small question. So you look at warp, and are there other ciphers that have like popular ciphers that have this the follow this GFN construction, and we probably looked to?
Yes, there is also Twine and L block, but we proved that they are quite optimal the permutation in them because we looked at the whole space of permutations of 16 elements. And we showed that the one in Twine and Warp are optimal.
Okay.
You couldn't do any better.
Okay, thank you.
Other question? So maybe I have one. So you have a new permutation for warp, and did you try applying existing tool to look at the resistance of your new proposal, or?
We didn't, because normally most of the attacks, that is non-related key attacks and non-invariant subspaces, are invariant in the equivalent classes, but this one is not equivalent. I don't know, we didn't do the analysis.
And do you expect that, for instance, I mean, for differential linear attack or for boomerang attack, it's still behaving the same, or?
It also depends on the number of active X boxes, and now the number of active X boxes is greater, so surely it improves the security against these attacks, but we didn't do the formal analysis.
Okay, and then if there's an attack where it would perform worse, what kind of attack would it be?
I think it can be related key attacks and also the one with invariant, because we didn't look at them at all.
Okay, thank you. Other question? If not, let's thank the speaker.
Hello, everyone. My name is Tianyu Zhang, a PhD student from Nanyang Technological University. Today, I'm going to present this work named Improved Mid-to-Middle Nostradamus Attack on AES-like Hashing. This is a collaboration with Xiaoyang Dong, Jianguo, Shunli, and Feng Fan. So this work is pretty much based on what Zhu has just presented before. So, okay, let me maybe give a quick introduction or a recap on what is introduced before by Nostradamus. So in Eurocrypt 2006, Kelsey and Kono shed light on this new security requirement for a cryptographic hash function that is called chosen target force prefix preimage resistance. So I won't tell a story, but I'll give a more formal definition about it. So it resembles the setting of a commitment scheme. So for a hash function h, it should be hard for the attacker to find a hash value ht or a commitment value for such that for any prefix s given by the challenger, he will be able to create a suffix such that the hash value of p concatenated with s will equal to this commitment value. So the generic CTFP preimage attack is known as the Nostradamus attack. So the evolution, the complexity of Nostradamus attack is first revised in 2012, and then it is extended into quantum setting at AsiaCrypt 2022. Then the previous work integrated the mid-in-the-middle attacks to the framework to achieve further acceleration. So the Nostradamus attack, as introduced before, consists two phases. So the offline phase is to build a diamond structure and with 2 to the power of k lives, and each node will be a hash value and each edge will be a message block that connects to hash value through the compression function. And a simple way of constructing those leaves will be fixing n minus k bits of those leaves as some constants, maybe all zeros, and then enumerate the rest k bits so that we can have a nice structure of those 2 to the power of k leaves. The online phase is to find a link to this diamond structure, and it's essentially a partial preimage attack. So we will first compute the initial hash value from the IV and the prefix P, and then find this M link that links this X0 to any of the leaf nodes of the stored diamond structure. And then we can simply look up the pathway and then construct this suffix. So the generic bounds of Nostradamus attack is given by the balance of these two online phase and offline phase. And you can see there's an important parameter k here, which denote the height of the diamond structure in logarithm 2. So in classic, the balance condition is k equals to n/3. And in quantum, because there's the complexity is a little bit different, so it's the balance condition is n/7. So in a previous work, so they use mid in the middle to accelerate this online phase so that it can shift the optimum to a more efficient overall time complexity, and that's the intuition. So maybe I will then introduce some preliminary knowledge of this work. First is the AES-like hashing, which has been repeatedly introduced during the conference, so I won't dig into the details. So it's basically the round function has this 4 operators, sub bytes, shift rows, mix columns, and net round key. I'm assuming this would be pretty clear for you guys right now. Then the mid-in-the-middle attacks is basically make use of the loop-like structure of a compression function inside a hash function. So find a way to partition this compression function nicely into 2 independent computable chunks. In this case, we'll call it forward and backward chunk that kind of meet in the middle at some matching point. And then what the attack do is we distribute degree of freedom or to find some nice candidates to both chunks and then compute to the matching point. And because there are some constraint incurred, so we can filter the candidate before checking a full match. And that's how it yields its advantage against a generic attack. So we will use, so because it's a very complex job to find this partition, so we'll use this automation tool. We model the propagation rules and the searching objective, and then we automatically run this algorithm to find the best attack strategy. So there are 3 kinds of bytes inside this mid-in-the-middle attack. So first is the neutral byte, which value of which is only known in the current byte, and it has 0 influence to the opposite chunk. So a blue byte will denote a neutral byte for the forward chunk, and the red will be the same as the backward chunk. And of course, there's some predefined constant valued chunks. So we will denote them as the constant byte, which is a gray cell right here. And then there are some unknown cells which denote that we have no control on the value of it, and the value is arbitrary, we cannot control it. So we denote it as a white byte, just for clarity. Then I'll introduce the main contribution of our work, which is the modified mid-in-the-middle framework. So we first review what has been done, and also as introduced by Zhiyu has before. So they use this mid-in-the-middle attack to accelerate the online phase. And as you can see, the complexity changes from 2 to the power of n minus k, which is the generic bound of searching a n minus k bit partial preimage, to 2 to the power of n minus tau. Tau here denote the advantage that mid-in-the-middle gives against a brute force search. So what they do is that they distribute some blue and red cells inside the target to provide additional degree of freedom, and also use this bytes to match the free bits inside of the diamond leaves. As we recall, there are n-k fixed bits and k free bits. So by doing this, they do this attack in the multi-target setting, but in other words, they're still looking for a true pre-image, but with maybe a slightly relaxed version. So this has refrained themselves from having any of the unknown bytes in the target. So it's a pretty strict restriction. So the diamond structure they finally built is dependent on how many blue and red cells they put inside this target. So what in this work, what we the main contribution of this work is that we actually extend this multi-target setting. An important observation would be we don't really need to search for a true pre-image, but we only need to match those n-k fixed bits marked in gray there, and the rest of them we don't really care. As long as we have a value of it, it's we can easily connect it to the diamond structure. So we have in a figurative way, we introduce those white bytes in the target and use all the non-gray bytes, white bytes, blue bytes, red bytes to match the free part. So we modify the objective, which we'll show later, and then expand the whole search base. And this has led to round improvements in AES and WRPL. So the refined complexity analysis. So as you can see in our work, we add in a new parameter KW here to track how many bits actually is not needed for in a partial matching. And then the diamond structure we build will be dependent on KW and blue and red bits in a target. So we will use this small example to showcase the effect of this modification. So on the left-hand side here, this is a figure from the previous paper. And as you can see, there's a blue byte inside the target, which will provide this multi-target matching. So in that case, K will equals to 8 because it's 1 byte. And then the advantage we get, this tau, the middle advantage we get will be the minimum of these three. So the dBdr stands for the remaining degree of freedom for blue and red cells, and M stands for degree of matching. So we did this small modification that will change one blue byte into a white byte. So after this modification, we actually we have the same K here. K will still equals to 8, but the advantage we get, we will first subtract 8 bits from the remaining degree of freedom of the blue cell. But because we are searching for a partial pre-image, we will add it in the front. So as you can see, this will be strictly bigger or equal to this tau, the previous advantage we get from the previous paper. So, so as a consequence, we applied this new model into the AES-like hashing. And in the classic setting, we are able to achieve a one-round breakthrough with a similar time complexity on AES MMO, and also 2 rounds improvement in WRPL in the classical setting. In a quantum setting, we're able to maintain the same time complexity at AES MMO, and in WRPL, we have a small improvement. And still, we applied the low QRAM technique in this DLPZ23, also mentioned by the previous work. And we construct this low QRAM variant of the attack. As you can see, we use a slightly more QRA QM, but we avoid using that so much QRA CM in this setting, which is 2 different quantum memories. Yeah. So that is all of my speech. And here are the reference, and thank you for listening.
Thank you for the talk. Do we have any questions? I don't see any questions, so I would have one. On the quantum memory, so you just on the last slide you just talked about it.
Yes.
So as you said, there is this version of the full Nostradamus attack, which runs without using quantum memory, so neither quantum random accessible classical memory or quantum memory. That's the one from the LPZ23. And in the dedicated attacks, such as your work and also the previous one we saw, you're able to use the the memory efficient offline phase. But in the online phase, it seems that you still need quantum memory, right?
Yes.
Do you think this would be, it could be possible to find a way to get rid of it?
Maybe, because in that case, we have to find a new framework for the online phase in the quantum mid-to-the-middle attacks, and maybe there are some future work could be done about it. Yeah.
Okay.
Yeah.
Okay. Or even like using only QRA-CM, for example, instead of QRA-QM.
Yeah, and I know there's a variant there, but yeah. So this, yeah, maybe we can work something about this. Yeah.
Okay.
Yeah.
Okay. Other questions? Okay, so I don't see any other questions. I think we can thank the speaker and all the other speakers of the session for the other one. So thanks a lot. And now we have